3.6 is all about derivatives of logarithmic functions. And it can get pretty involved with the algebra. And so we're going to split it up into a couple days. So the first day, we're just going to introduce the very basic derivatives of log functions. And in your book, there are plenty of proofs, but I'm just going to present them to you. If you're really curious where they come from, page 218 is where all that stuff lives as far as proofs go. The first one to look at is basic derivative of a log. It could be any base and of some number. So log base b of x. And the derivative of that is going to be 1 over x. So this number here goes on the bottom, and then you have to multiply that bottom by the natural log of b. Like I said, in the book, it goes through all the different proofs as to why it switches from log to natural log and that kind of thing, if you're interested in that. But this is a formula you're going to need to know. The next one is definitely one you need to know and is fairly common. And that is the derivative of the natural log, and that's just 1 over x. Pretty straightforward. Again, same page. It's on 218 in your book. The last one is on page 220, I want to say, and that's the derivative of the natural log of the absolute value of x. That actually is also 1 over x. And on 220, they go through right side and left sided limits, I believe, and go through why that all works that way. And you can kind of see for yourself why that does. Either way, in reality, you basically have two different formulas to memorize, since the outcomes of these two are the same. So let's talk about some cases where the problem is a little more involved, right? As you notice here with these two examples, they look similar to what we had before, but now instead of having just an x here, we have an actual function, which means there's a chain rule effect, okay? So if we think about what the actual formulas are, here's how it differs, okay? And so for this one, the derivative log base a of g of x, it's going to start off the same. So I'm going to go 1 over the g of x goes in place of the x, and this is the natural log, the natural log of a. But I also have to multiply by the derivative of that function because of the chain rule. And so in the end, what I end up with when I have log base a of a function is I have the derivative of the function over g of x times the natural log. I did it again. Natural log of a. Okay. It's going to work the exact same way for this other example. Since the derivative of the natural log is 1 over x, this is going to be 1 over g of x, but then I have to multiply that by the derivative of g of x. So in reality, the derivative of the natural log of g of x is g prime of x all over g of x. The only difference between this problem, where I have just an x here or I have just an x here, is instead of having a function, I have this inside, okay? So the inside function is the g of x, and that's why we have to have that additional derivative of g of x being multiplied by what we have for the outside function using the formula. Now we're going to go through several examples, and I'm going to do this a little bit differently than I would normally during class. I'm going to do the problems with you rather than have them done ahead of time. So I'll try to go slow with it, and if you have a question, make a comment in your notes, then shoot me an email and I'll do my best to get back to you. So here are our first two examples. The first one, f of x equals log base 5 of x times e to the x. And our second example is f of x equals the natural log of x squared plus 10. So these start off the same as the last problem. You just used a formula and then had to use the chain. this really is all what's going on here, is instead of having just an x here or an x here, I have another function here. So I'm going to end up having to take the derivative of this as well and multiply by what we get from the formula. Same with this one. So my formula is, we want to be sure to indicate that we're taking the derivative, and I'll move this up. So this is going to be 1 over x e to the x times the natural log of 5. And then I have to take the derivative of x e to the x, and that's going to involve the product rule. So the product rule says take the first function, just write it down, and then multiply it by the derivative of the second function, which is still e to the x. Add to this e to the x, the second function, times the derivative of the first function. So I can take all this, just kind of move it up so you guys can see it a little better. And now we have to simplify. So the top ends up being all of this. And it's possible that we might be able to cancel something, and we'll see how this goes as we work through it. Again, I'll move this up. So f prime is x e to the x plus e to the x on top over x e to the x natural log of 5. And so hopefully you're seeing that we're going to be able to do some canceling here. Since I have e to the x in all three terms, I can cancel those out. And so my final simplified answer is going to be f prime is x plus 1 over x times natural log of 5. Another way to think about this is if I factor an e to the x out, and that leaves me with x plus 1, and then the e to the x's cancel. This next one's going to work very similar. Again, f prime is going to be 1 over x squared plus 10, but then I have to take the derivative of this inside function. And so when I do that, this gives me 2x. The derivative of that is just 0. And so I'm multiplying by 2x. And so I can clean this up a little bit, but not a lot. So 2x goes to the top. X squared plus 10 stays on the bottom. I cannot cancel. This is a group. Unless there's an x over here, I can't just cancel those. So that's where we're going to land for this one. Again, just using the formula, the derivative of the natural log is 1 over x. Over here, the derivative of a log base is 1 over x, or whatever we have here, times the natural log of 5. So those two aren't too bad. Let's look at the next two. Again, it's the same idea, and I mentioned this the other day. I know that we separate the idea of the product rule and the quotient rule and the power rule as sort of separate standing rules, but hopefully you're starting to see why the chain rule is just sort of always involved, or can always be involved in any of these problems. And once you start looking further inside and inside, you can see that more differentiation needs to happen in some of those cases. This is going to be one of those cases, right? So now we're going to connect together our trig functions, our natural log functions, and the derivatives of those. So for this one, okay, of course we know that the derivative of the cosine function is negative sine, and it's of whatever we started with. The trick is now that I have to multiply this by the derivative of the natural log of x, which is just 1 over x. And so I can clean this all up a little bit, and now I have the derivative of f. Let's see, so this is going to be negative sine x of, sorry, not x, my bad, the negative sine of the natural log of x all over x. And that's using trig functions, using our natural log functions, and using the chain rule. And so this, again, this is not the sine times. This is the sine of the natural log of x. So if x was a number, like you could punch this all in your calculator, it would give you an actual numerical value. Okay. This next d is the same kind of thing. I have f prime of x. This is 1 over sine squared x, because the derivative of the natural log is 1 over x. But then I have to multiply by the derivative of sine squared, which is going to involve chain rule a couple times. So I'm going to slide this over a little bit and then separate that. So what that means is I'm going to take the derivative of sine squared x. And so I have to first use the power rule, so that's 2 sine x. But then I also have to multiply by the derivative of the sine, because now the inside function is the sine, and so I have to multiply that by the cosine. So we have a double chain rule here. We have 2 inside functions. The first inside function is sine squared, because that's inside the natural log. Then I have to take the derivative of the inside function, which means I have another inside function, the sine, and that's where the cosine comes from. From here, I can clean this up a little bit more as well, and this one's going to work out okay. It's going to clean up even more. So I've got sine x, cosine x, 2 sine x, cosine x, and then sine squared x. So I can cancel the sine and the squared. And so what does that leave me? That's 2 cosine x over sine x, and we know that that is the cotangent of x. So again, as we've been talking about all year, you want to be able to flow between these two, because on a multiple choice question, this might not be a response and this might be. So it's important to be able to flow between those two. All right, the next two, it's the same idea now. We're just using the chain rule along with some of our new functions. And so, you know, if you want to just pause the video and try these two yourself, and then let's see how you end up. Yeah, why don't you do that? Go ahead and pause the video, try these two yourself, and then when you're done, I'll do one at a time, so you can, if you want to clean it up and look at this one first, it won't all pop up on the screen. All right, of course, my first move is to change this problem to the natural log of x to the 1/5. And so I'm going to show you a couple things that would make this problem a lot easier if you wanted to do it that way. I'm guessing you didn't do it that way, though. So I'm going to do it the way I think you did it first, and then I'll show you the easier way for this particular problem. It doesn't always work, but for this particular problem. So I could, again, using my natural log derivative functions and chain rule, okay, f prime is going to be 1 over x to the 1/5. And then again, I have a function here, so I have to take the derivative of that using the chain rule. So that's 1/5 x to the negative 4/5. So then it's a matter of cleaning all this up. Okay, so here's where I'm going to go with that. First of all, this 5 from the 1/5 can just go on the bottom. And it can go, it can go down there with the 1/5. And the 1 stays on top. And then the other thing I'm going to do is move this down. So that becomes x to the 4/5. Well, fortunately for us, that cleans up kind of nicely. This is 1 over 5x. 1/5 plus 4/5 is 1. Now, if I were to guess, you did it this way. Let me show you another way using log properties. Okay, let me get rid of all these. So knowing our log properties, whenever I take the log of a function and there's a power, I can use the power rule. And in reality, this is the same thing as 1/5 times the natural log of x. And so then I take the derivative. Here's my constant that I can kind of sort of ignore, just kind of hangs around, and then I take the derivative of this, and this is 1 over x. So this all gets me to 1 over 5x. Two ways to get at the same problem. To me, this one seems a lot easier than having to use the chain rule and then deal with all those powers and the negatives and that kind of thing. So my recommendation is, when you see something like this, use your power rule, because that'll make that problem a lot easier. And we're going to get to using the different log rules again on day 2 quite a bit, actually. So it's a good little refresher. Now, I don't think we have the luxury over here of anything like that. We're still going to have to go through that same thing. So again, if you've only done the first problem, pause it, work on the second problem, and then come back and I'll go through this one. Okay, so this one, again, g prime of x. Actually, I'm going to give it a little more space just because it looks like we're going to have a couple chain rules here. All right, so I've got 1 over, remember, the derivative of the natural log of the absolute value is still 1 over x, or still 1 over this. So in terms of worrying about that, it's not too big of a deal. Now I've got a double chain rule here, because I have the tangent as an inside function and the 2x as an inside function. So when I take the derivative of tangent of 2x, that of course is secant squared 2x, and then I have to take the derivative of 2x. So now it's a matter of trying to clean this all up, and here's where we're at. So I've got 2 secant squared 2x over tangent of 2x. And maybe you're thinking there's a way to simplify that, the secant and the tangent's cosine, sine over cosine, and the secant is 1 over cosine. And so this really would be 1 over cosine squared. And so, and then since this is on the bottom, I'd have to flip it anyway. This is like the cotangent. And so that would be cosine over sine. All right, so let's play around with this a little bit. So I've got, let's see, 2, and I'm gonna make this cosine squared 2x. That's this. Then since this is sine over cosine, but it's on the bottom, I flip it, it becomes cosine, oops, it should be 2x, cosine sine. So I guess I get 1 cosine to cancel, but then I'm still left with a cosine. Again, it goes back to that same idea. This can go, one of those can go, and I'm just left with 2 over cosine 2x sine 2x. So again, this would probably be like a homework quiz, that kind of thing. I'm not sure that this is really any better than that. But it can be done. You can simplify a little bit. Again, the reason that I put this here, just in case you're wondering about this, you're like, wait, this is sine over cosine on the bottom. It's keep, change, flip. I'm dividing by a fraction, which is the same as multiplying by its reciprocal. And so that's why I did it like that. And I could see that the cosine would cancel. It'd give me a little bit of relief, not a ton. All right, next one. And even though we talked about avoiding the quotient rule, I'm going to use the quotient rule for this one. I could make this 1 minus natural log of t all raised to the negative 1 power and then use the product rule. But I think it's good to practice the quotient rule once in a while. So here we go. Again, pause it if you want. Actually, this one's not too bad. There's no chain rule stuff going on because it's the natural log of t. But yeah, pause it if you want, and then come back and we can go. You can see if you did it right. All right. So I've got f prime of t. Now I'm doing low, d high. So the derivative of 1 is 0. The derivative of natural log is 1 over t. Low d high minus high. Derivative of low is just going to be 0 minus 1 over t. So negative 1 over t over, don't forget the low squared. Okay, so now we got to clean this up, expand the top, see where we get. And actually, before I expand the top, what I think I'm going to do, because here's what I'm thinking. You could do this. You could distribute, but because they both have 1 over t's, and then maybe something's going to cancel in here. So what I'm going to do is I'm going to factor it out. Let's factor out the 1 over t, and let's see where that gets us. So I've got 1 over t on top. Okay, 1 minus natural log of t. Now, here's another little trick that I'm going to be able to do in one move. Okay, since I'm going to be left with a minus, and I already have a minus, this is going to change to plus 1 plus natural log of t. And this is all being multiplied by 1 over t. So that's the factoring piece. Okay, when I factor that out, I'm left with these two things. Again, if you don't like this, you can distribute, and you can do the problem the same way. Okay, and then the bottom is still the bottom. 1 minus natural log of t quantity squared. And so then what do I get here? I've got on top, actually now I'm going to throw the t down. I'm going to move this t down to the bottom, down to here. Okay, and then here I've got, it looks like 1 plus 1, and then the natural logs are going to cancel out. So again, t on the bottom, and I got 1 minus natural log t quantity squared. That's all on the bottom. And then on top, all I have is a 2. Okay. So if we think about it this way, right? Since this is plus, these parentheses are no longer needed. And then the natural logs cancel. So yeah, that's, I think, as far as we can go with that. You would get the same exact answer if you distributed up here, because if you notice here, this would be a plus natural log of t over t and a minus natural log of t over t. Those would cancel out. I would have 1 over t plus 1 over t, which is 2 over t. There's my 2 over t. So either way, it works the same thing. Okay, you'll get the same answer. All right, one more problem that we need to look at. So here's a function. Find the domain, and then find the derivative. So go ahead and do that. Find the domain. Okay, we obviously have a fraction here, so we're worried about this becoming 0. Right? And so if this becomes 0, and also one other thing. What is true? What was true about the number that has to be here next to the natural log? Think about those two things, try to put them together, and see if you can come up with the domain. Okay, so the first thing we need to consider here is this natural log. This number always has to be positive. So we're starting here. We're starting with this idea. X has to be greater than 0. Now, the question is there ever a time when the natural log can be a negative number? And x is also positive. So remember, we're saying e to what power equals this. So what I can have negative powers because e is a positive number. So even if I raise e to a negative power, it still stays positive, but it just puts it in the bottom of a fraction. So for example, e to the negative 2 is the same as 1 over e squared, Well, e squared is 2.7 whatever to the second. So as that number on that negative number that the power is raised to, this value, because the power is what this is all equivalent to, just gets smaller and smaller. The question is, can this ever equal -1? Can the natural log of x, this is the question where I'm asking, okay? Can the natural log of x equal -1? Because if it can, then this becomes 0, and that would be a value we'd have to exclude. Well, I think it's fairly obvious of what that is. It's just e to the -1, right? Because if you think about your old, when we first learned about logarithms, this means e to the -1 equals x. Well, that means e to the -1 would be a value that would create a problem here. Is e to the -1 positive? And the answer is yes. Okay, so not only does x have to be greater than 0, but it cannot equal e to the -1. So let's break that all down again, because really what we're talking about here is this is the natural log of e to the -1. And we've learned about we talked about the power rules. Let's just deal with that. Bring the power out in front. Well, the natural log of e is e. These kind of cancel out. And so there is a case where we could have an issue. All right, so now how do I put this all together to write the domain? Could I write this? I mean, e to the -1 is a positive number, and it is greater than 0. So another way that we could write this domain, maybe this would be the best way to do it. If we said an interval, here's the domain. I guess we wouldn't write it using set notation. We would go like this. We would say 0, because it can't equal 0, but it's got to be bigger than 0. It's got to be positive. To e to the -1, open parenthesis, union e to the -1 to positive infinity. So basically what this is saying is exclude e to the -1. I guess if you were doing it in set notation, you could write it like this with almost like a comma. So let's do it that way too. Either one is fine. Yeah, probably if we're going to do it really correct, we should do it like this. It's got to be x to the -0, and the exception is x cannot equal e to the -1. Both of those say the same thing. Whichever way you want to do it is fine with me. Okay. All right, now we have to find the derivative of all of this. And in this case, I am not going to use the quotient rule. I'm going to use the product rule. Actually, I'm going to use the power rule, and you'll see how I do that here in a sec. I think I'm going to use the next slide because I've run out of room here. Okay, let's get rid of all this. And now we'll take the derivative. So here's what I'm talking about. I'm going to make this f of x equals 1 plus natural log of x to the -1. All right, so I can just use the power rule here, and then also the chain rule, because I'll have to take the derivative of the inside function. All right, so the first derivative is going to be -1 times 1 plus natural log of x, reduce the power by 1, and then I have to multiply by the derivative of the inside. This is 0, this is 1 over x. So let's see where that gives me after we clean this up a little bit. All right, so I've got an x on the bottom. I've got a 1 plus natural log of x squared on the bottom. And I guess I just have a -1 up here. This should all go under. So there you go. So a couple new properties, new rules with the log and the natural log. Otherwise, it's still using all the different differentiation rules and properties that we've had before. Okay. So let's see. If you want to email me tonight, I'll be available. I won't be at school again tomorrow, but I will see email, I can get back to you, and then we can go from there.